So everybody's ready. I'm recording this and then I'm going to share my screen. And as I mentioned earlier, we're going to start with this, the foundations of regression, which is the science behind multiple linear regression. There's two of them, the ordinary least square and the maximum likelihood theory. So I think it's very important to talk about ordinary least square because this is really the basic mathematics of regression. So this is a slide available. Made available by Stanford University. Stanford actually offers a free statistics. If you like to learn more, you can enroll in their online called World Academy or an open community learning. And you can enroll in their advanced statistics class online for free. And you get a certificate of completion. It's really up to you if you want to enrich yourself, but these are some of the things of a lot of rich university here in America are offering all this free online, and you can be in India, you can be in the Philippines, and as long as you commit yourself to the online learning, they're offering it online, believe it or not. So that's a very different model that I've learned here in the United States. I did try 2 years ago to apply to all this online, and it was really helpful, even though it's quite complex and difficult, but it's very helpful. Okay, so let's start with what is ordinary least square, or OLS, or simply known as linear regression. And as I mentioned earlier, you can actually get the same analytic results by doing ANOVA, which is analysis of variance, and simple linear regressions. So as long as you appropriately model your research question and your theory. So as I've mentioned also in the first week, that in the past, there were really a group of ANOVA researchers, and everything that they do when they analyze data, they use ANOVA, analysis of variance. And there are a group of researchers in the past in the United States where they're called the regression researchers. And whatever data they have, they're going to use regressions in their analysis. And so there were two camps of researchers, but now the modern statistical world really is looking for a unified look into this different statistical analysis, and trying to really emphasize now that you can really use either. It's not both or all or nothing approach. You can really use either one of them as long as you appropriately model your theoretical assumptions. So let's start with OLS, because this is the foundation of linear regression, or generalized linear modeling. So from the word itself, GLM, generalized linear, so there are really assumptions that are very deeply rooted to the analysis and the mathematical formula of this approach of analysis. So we're gonna first, this is the outline. We're gonna really look at linear regression. So it's line. So we are simply putting a line, and we assume that the data will represent this line. Okay, so it could be it's just a straight line. And of course, the middle, when you have your y-axis and your x-axis, you draw the line in the middle between these two axes, your y and your x-axis. And between that, it will create an intercept. So that's basically what we need to understand, that there are intercepts, and these intercepts will be called coefficients. And then the model will assume and will also need to be checked for different interactions of these independent variables that affects the different value of the intercept leading to the outcome. Because remember, the tip of the line is our dependent variable. So for example, if I'm interested in decision satisfaction, and there are two outcomes for decision satisfaction in cancer treatment. It's satisfaction, and then the other one is dissatisfaction. So it's a binary dependent variable, and it's very perfect for logistic regression, because logistic means two outcomes only, two binary outcomes, which I will also cover later on. But the fundamental science of logistic regression, multinomial logistic regression is really OLS. It's linear regression. So we need to cover linear regression tonight. And then we're going to look at the geometry of least squares. And then we're going to look at also and discuss the Gauss-Markov Theorem, which is the basis, the mathematical basis of OLS. So when, as I've said again, you have your model, and it will be represented by your y and your x-axis, and you have your beta and your alpha, and you have your, all of this that are found here are considered your data, and these are your independent variables. It could be one-dimensional, which is, you know, if I say my dependent variable right here towards the end would be satisfaction of the decision, and then my independent variable are how well did the patient participate in the decision making. Okay, and then if I will say that is an independent variable that's ordinal or scale. So remember that we have different types of data, so that's why we go back to the statistics one, that the levels of data are nominal, ordinal, interval, and then scale. As long as your data type is ordinal, interval, or ratio, which is the scale. Ratio has the zero natural point. As long as your independent variable are having those characteristics of data, you can plug them in as your independent variable right here. So you cannot use nominal variable in a one-dimensional regression. Okay, so in one-dimensional regression, where we look at the relationship between an independent variable and a dependent variable, if it's using the linear regression, we need to have a continuous variable, which could be either ordinal, interval, or ratio type of data. And so this is what linear relationship, or the best linear relationship, looks like. It's that the beta, or what we call the coefficient, is equals to the alpha times the error, and with the independent variables. And so that's the best linear relationship that we could ever get. And what happened then is that in one-dimensional regression, we can see a problem where the data does not go through a line, which is expressed by your, this is your expected error, is equal to the beta minus the alpha of the x or different independent variables. And so you can see here when there's a lot of data that is leaning towards the beta, this is how it's being represented. And here, in order to correct the problem, we will find a line that minimizes that error in the beta area, or what we've called the coefficients. And so the best solution to the problem, to the first limitation of one-dimensional regression then, is to find the sum of the squares of the beta minus the alpha, and it's multiplied by the error. So when we look at the expected error, we're going to square the sum of the beta minus the alpha and all the independent sample error. Now, these are really complex mathematical notations, but I have prepared some explanations of this, and that is the Gauss-Markov Theorem that explains this. And right here, I will send this to you all. It's actually a 73-page reading, but the first 2 pages are the most important one because it has the full ideal conditions of ordinary least squares according to the Gauss-Markov theorem, or according to the Gauss-Markov assumption. So this is really a very good descriptive summary of the Gauss-Markov theorem. I could just emphasize to you what are the highlights of the Gauss-Markov assumptions, because you can read this in details later on. So it talks about full ideal condition, or what we call the blue, the best linear unbiased. It's the estimator. That's why it's called blue. It's an abbreviation. Blue is, so this is the ideal, full ideal condition, is that the OLS is the best linear unbiased estimator. So that is the highlight of the Gauss-Markov theorem, that in the full ideal condition with the collections of this assumption and using the regression model, the line model, the linear, generalized linear model, and the data generated from this process can be thought as a description of the ideal set. We think that this is the ideal, how the data, see, ideal is the theory that we are aiming for. And so that's the theoretical framework where we base our measurement as well. And so that's represented by this mathematics of Gauss-Markov assumption. However, we know that in reality, not all of these conditions will be met in an experiment. So what are the different things then that we can do to really get or maximize the functions of the OLS? And remember, from the word, it's estimator. So what it tells you is that it tries to correct as much as possible whatever error there is. So that's the job of the ordinary least square mathematics. So one has to be aware of the ideal conditions and the different violations, because if we know the possible violations to this assumption, then we can control them, control the deviations from this condition that may render your results unbiased or least consistent. That's why we call this ordinary least square. And the theorem is Gauss-Markov Theorem. And again, the key concept is that this is your best linear unbiased estimator. So the key word here is that it's an estimator. We try to really get the best conclusion that we can get using this, this model. The first assumption is that right here, number one is that the linearity in the parameters in the alpha and beta is that the dependent variable is a linear function of a set of independent variable and a random error component. So remember that the random error is represented by X. In the model that I've shown you here, so this is a very important concept as we go back to this, is that right here, this is your random error, and B is for your beta, and A is for your alpha. And then this is your expected error. And then, so when we go back to this, very important first assumption is that your dependent variable, for example, my dependent variable is satisfaction versus dissatisfaction. I have only two. And then my independent variable is the level of participation of the patient. For example, I have 3 levels that are ordinal in data. It's the patient is, 1 is denoted by, I would say, not interested in participation or passive. And 2 is considered as shared. If I score the patient's participation as shared, the patient wants some of participation, but also want half of the decision to be done by the physician. And then if I put 3 as active, which means that the patient wants all the decisions. This is, so I have this ordinal. I have 1, 2, and 3 levels, ordinal levels. And I want to know that my model, that the assumption is that there is linearity in parameters of the alpha and beta, and that the dependent variable is a linear function of a set of independent variable and a random error component. So here, that is a very important definition when we look at this simple one-dimensional regression. So if these are my data, I have patients who put 1, who answered 2, who answered 3, because 1 is passive, 2 is shared, and 3 is active. And the definitions of those are that active is that the patient just want to make all the decisions. And then I want to find out how this ordinal value that I gathered from my patient leads to dependent variable, which could only be satisfaction or dissatisfaction. And so all of this represents my collection of data of the ordinal values, 1, 2, and 3. So the question then in the model for one-dimensional regression is, what is the relationship of patients' preferences for decision-making, for participation, to the dependent variable, which is the satisfaction versus dissatisfaction with the decision, with the cancer treatment decision. So, and then right here, again, we put the line that best represents this best linear relationship. Is it the higher the level of participation of the patient will result to higher satisfaction? So the hypothesis our hypothesis is always, our null hypothesis for one-dimensional regression is that there is no relationship between the independent variable and the dependent variable. So this is at the minimum when we look at one-dimensional regression. We are looking at relationship, but at the same time, when we look at different regression models, we are also, by the time we get to multiple independent variables, we're also going to look at the predictive analysis or the predictive power of the independent variable towards the achievement of the dependent variable. So right here, so this is the problem, that if the data does not go through a line, so you will have errors then. So that's your beta minus your, according to the assumption, the random error component of the independent variable, and therefore it's represented by beta minus all the independent variable and the random component. And that is the best representation of a one-dimensional regression. And then we square the sum of the beta minus the alpha and its random error component. And then we get the blue, or what we call the best linear unbiased estimator result. And that's represented by our coefficient. So this is the assumption number 2, is that the expected value of the error term is 0. So we really expect in a perfect world, there should be no error, right? But that's never true when we do experiment. That's never true when we measure a construct. That's never true that when we give questionnaire to our patient, that there are no errors in all of those aspects. So we do need to account for those errors. The other assumption is called the homoskedasticity. This is when I was in my statistics class, it was really something that until now, I'm still reminded, it's really the homogeneity of the variance. I think that you all have looked at this, and even in ANOVA, remember that one of the assumptions of ANOVA is homogeneity of the variance, and there is a specific statistics that we need to look at when we interpret ANOVA. So anybody could still remember that? What is the statistics that we look at in ANOVA that will tell us that the null hypothesis is rejected? Is not, it needs to be, because remember our null hypothesis for homogeneity of the variance, that there are no differences in the variance of the samples. And so that's the homogeneity of the variance. That's for ANOVA. It's the same thing with linear regression. There has to be homoskedasticity of the data. And so it implies that the model uncertainty is identical across observations. So there's a lot of similarity here, because remember that we have ANOVA researchers and we also have regression researchers. So I need you to remember that when you analyze your final exam last quarter, there was a question about, which of the statistics look at the homogeneity of the variance, and that it should not be statistically significant, so that the null hypothesis that says that the variance is homogeneous is retained, or else you're not meeting the assumption of ANOVA. So right here now, also in linear regression, because we are using the same theoretical understanding or underpinnings that there is homoskedasticity or homogeneity of the variance. So this is again a very important concept. So what could be the potential problem? Well, it's the heteroskedasticity of the data, or what we actually rejected the null hypothesis. If we use the ANOVA, it shows that the variance is heterogeneous. So this is the equivalent. It's problematic. Remember, you cannot use ANOVA. You cannot use ANOVA if it does not meet the assumption of the homogeneity of the variance. And what is the alternative if we don't meet the assumption of ANOVA? If we have to do the non-parametric Kruskal-Wallis. That was one of your exam questions in the finals, is to use Kruskal-Wallis statistics for those, if your data set does not meet the homogeneity of the variance, which is an assumption, an important assumptions of ANOVA. So right here, if there's a problem with heteroskedasticity, which is often a problem in cross-sectional data, you might have an observational bias. And again, in linear regression, the major cause of heteroskedasticity are the outliers, and we need to remove those in linear regression. There is no alternative, unlike in ANOVA, that when you don't meet the homogeneity of the variance assumption, you can use Kruskal-Wallis statistics. But here, in linear regression, if there is heteroskedasticity, what we need to do is try to remove those observations and meet the assumption of linear regression. Okay, because remember, this is an assumption that there has to be homoskedasticity of the data sets, of all the observations. And the fourth assumption is that the error term is independently distributed and not correlated, that no correlation between observations of the dependent variables. So again, looking at collinearity is an important assumption in linear regression for OLS, the ordinary least squares. We do have a problem when there is spatial, right here, we will have a problem if we see spatial correlations, that is in what happens in panel or cross-sectional data, serial correlation or autocorrelation, such as in panel and time series data. So these are some of the things, that the potential error that we need to control when we use ordinary least squares. And then number 5 is that the independent variable is deterministic, that the X is uncorrelated with the error term, since all of the independent variable is deterministic. So potential problems are omitted variable bias, endogeneity, and simultaneity. And so we are going to look at, again, collinearity, multilinearity, and existence of many other potential problems, such as measurement errors, inconsistency of using the same tool, inconsistency of using the same standards of the equipment of your experiment, and multicollinearity of the independent variables. So they have very, very strong association with each other. And that's what you call multicollinearity. So you have three, four variables that have very, very strong relationships to the dependent variable, and multi-collinearity exists, and that's a potential problem. So it is important that our observations or our independent variable are that's why it's called independent variable, okay? So that is an important concept. These are the 5 important concepts in ordinary least square, that your independent variable is uncorrelated, and that the error term, which is expressed by xi, the error term of your independent variable, is deterministic. So this is the basic concepts of ordinary least square. And I'd like you to think about the characteristics of ANOVA, because remember that ANOVA researchers in the past are one group and the other group are regression researchers. So there's definitely similarities in the underpinnings of this statistical analytic methods and procedures. So this is the Markov theorem. Again, so the Gauss-Markov theorem is looking at optimality at all time. As I've mentioned, we're looking at the achievement of blue, which is your best linear and bias estimator, BLUE. And these are the different mathematical definitions of that theorem. And again, it expects that the error is 0, that the independent variables are deterministic, and also the errors right here, that the error term of all the independent variable is also deterministic, so that all of your variables are independent, all of your data are independent with each other. And that's best represented by this mathematical expression. And that gives you the product of linear regression, which is blue, best and bias linear estimator. And this is a very good representation. Basically, what happens to your data when your error term is 0. When you have a 0 error term, it looks very pretty, and your independent variable is strongly correlated to your dependent variables. So I would say that if the higher the level of participation of the patient, the higher is the satisfaction. That should be represented by my linear regression. So if my respondents, if I have 1,000 patients, and these are the one who answered 1, they are positive, but there's a lot of patients that answered towards 3, which is the active participation, and that leads to satisfaction of the decision, higher satisfaction of the decision. So that is that the error term of my observations and that there is homogeneity of the variance. So my data is really best represented by a line. Then I've got blue. That's the ideal picture, right? That's the ideal situation in an experiment, that if I have 1,000 patients that I've asked ordinal data from 1 to 3, 1 is passive, 2 is shared, and 3 is active decision making, and it leads to satisfaction with their treatment, cancer treatment decisions. That is the perfect ideal situations, and that my error term is 0. But that can't be the situation.